Good afternoon, comrades and friends. Thank you so much for coming. We call this talk Something Rotten in the State of Data Centers, which is just a tongue-in-cheek way of saying that we found a lot of ODAs in device management software that's commonly found in data centers, and we're very excited to be here to finally talk about it. So I'm Jesse Chick. I'm a vulnerability researcher, and I'm actually currently looking for a new gig. So if you like what you see and could make use of somebody with my skill set, I'd love to talk. You know where to find me. And
I'm Kasimir Schulz. I'm a principal security researcher over at Hidden Layer. If you want to talk to me about this research or any of my other research, you can contact me on Twitter or LinkedIn. Let's get started.
So just a quick roadmap of the ground that we're going to be covering here today. We'll first of all justify data centers as a viable inquiry for research, line of inquiry. And then Kasimir will talk about our first target, which is a DDI solution for all things IP addresses. And then I'll take us over to the hardware side and talk about a KVM. That is not a kernel virtual machine, by the way, just to disambiguate terms. And then we'll leave you with some closing remarks and key takeaways. So jumping right into it, why data centers? Well, there really isn't anybody out there whose digital life is not affected one way or another by data center security. It's very much at the intersection of corporate and governmental concerns, which makes it a very high impact vector for threat actors. So we like to do the most relevant research that we can, generates buzz, tends to be more interesting for us from a technical perspective, so that's why we showed up here. And it also happens to be of significant national interest, and at risk at sounding overly provincial, the US government has recently been taking a heightened interest in data center security, trying to raise that threshold, and I've been made aware that similar efforts are going on in the United Kingdom and throughout the rest of the Western world. We also noticed that there's very little end-to-end, like publicly available vuln research in this space. So we kind of wanted to tap a little bit of new ground, at least as far as publicly disclosed stuff goes. And on the whole, as we suspected, a lot of these devices are every bit as vulnerable as the others that you see in everyday life. So if you're interested, we won't dwell here. You can check out the talk that Sam Quinn and I gave at DEF CON that covered the power management component of this larger research effort on the part of our former team. And with that, I will hand it over to Kaz to talk about our software hack.
Thank you, Jesse. So to get started with what you're all here for, 0 days, right? Everyone wants to hear about 0 days. So we're going to get started with the software side of things. So as Jesse mentioned, today we have software and hardware. So let's get started. What some of you might have noticed in our outline slide is that we said mystery vendor. And the reason for that is there were some delays in responsible disclosure. So the first target is just going to be referred to as Project X. We were very lucky that the vendor was kind enough to actually let us continue doing the talk despite the delays. So we just want to give them a thank you. So Project X. Project X is a DDI, and for those of you that don't know, a DDI is a solution that integrates DNS, DHCP, and IPAM. Don't worry, I'll go over those in a second. So DDIs are great. They're really, they provide efficient and secure network management for any networks that have a lot of devices, and data centers tend to be like that. So DDIs make a great resource for data centers. DDIs have 3 components. The first is the DNS, which provides easy and reliable access to resources. By adding domain names instead of IP addresses, it makes everything a lot easier to access. DHCP, on the other hand, automates the assignment of IP addresses to devices. And then finally, we have IPAM, which helps manage and organize unique IP addresses to specific devices. So let's say that you have one device that always has to have a very unique IP address and it can't change. That's when you would use IPAM to manage that. So now that we've talked about what Project X is, let's actually talk about the architecture of Project X. So Project X is split into 2 main components, the web server and the control server. The web server hosts the management website, so that means anything you want to do on the control server, so if you want to set up DNS, DHCP, anything like that, has to go through the web server. That means it also handles all the user interactions and session management. And the reason why it handles session management is because it can be connected to multiple different control servers. So that means one web server can be used to control 2, 3, however many control servers you want. Control servers, on the other hand, control all the individual components. So that means it's in charge of the actual DNS, the DHCP, everything like that. And since the web server can be used to authenticate against multiple different control servers, the control server is what actually controls the authentication. So that means while the web server handles all the session management, the control server is used. Otherwise, you'd be able to authenticate against any server, which would be bad. And then finally, the control server also handles all logging. And while this might not seem important now, it is fairly important, and we'll get into that in a second. As some of you might have seen in our outline, we had a fairly complete attack chain, and that was centered around our authenticated command injection. And I know what you're thinking, authenticated is probably not really a full attack chain, but trust me, it'll get good. So the way that our authenticated command injection worked is that the web server had a system where admins could run scripts on the control server. These scripts had to be manually added to the control server, so none of that could be added remotely. So that in itself was not really an attack path, since you had to actually have physical access. The way that the system worked is that it was almost an event hook. So you would set up this hook, and then you'd tell it what type of events to trigger on. So that's if an IP range was added, things like that. And the way that it worked is that you gave the hook a script name, and that script name had to exist in that folder. What the control server then did is if the event was triggered, the control server would just run a shell with that script name, and that's where their command injection came in. No validation was done at all on either the web server or the control server, which meant that we could input whatever we wanted. And here's just an example of what we kind of inputted. So as you can see, since we were able to input whatever, we just used Python-C. When we were originally testing this, we did use open and then a file write because that's a little bit easier to see. However, that did not fit on the slides, so we scaled it back down, and that's why logging is important, because we were able to print and then check in the logs that it was also still valid. Now, an authenticated command injection, while it's great that you get remote code execution, it's not very useful, especially if you need admin access and there's only 1 or 2 admin accounts. So what we did is we decided to try to find a way to bypass authentication. And as reverse engineers, before we can actually bypass anything, we have to go and figure out how it works. So we did that, and I'm going to talk about that a bit. So as I mentioned, the web server can contact multiple different control servers and manage them. So when the user at first messages the web server to connect to a control server, they have to give them the server IP as well as the user credentials where they're trying to log in. The web server will then initiate an HTTPS request over to the control server, which then validates the credentials. And then rather than responding right away, what the control server does is it directly connects to an open port on the web server, which I see a few eyes are kind of happy there about an open port, and that's valid. So once the web server then actually receives that direct connection, it tries to establish a session. It generates a session ID, which is then sent back to the control server. And then all the control server does is it logs that session ID and then sends it back as a response to the original HTTPS request, which is then received by the web server. And then both of these can then use the session ID to authenticate against each other. What's important to note here is that the control server does not need any authentication after this point. So as long as you have the session ID, any requests from any location, so you don't even have to go through the web server, as long as the session ID is in there, you can control anything and do the authenticated command injection. So now that we've talked about the general authentication process here, there's still that black box item. We don't know how session ID is generated, and that's the important part. We need to see if there's some way that we can make our own or fake it. So let's talk about the generation of session IDs. As I mentioned earlier, when the control server responds to or connects to the web server, it tries to create a session. And this is some of the code from the web server. So there's this add session function, and in here, they built this custom random and this custom ran string function. And the way that it works is when you initially connect and the session is created, it will then initialize the random function, and it does that for every single connection. And then it will call that ran string function to actually generate the session ID. And while this was, in theory, a fairly good authentication process and a way to create session IDs, there was a fatal flaw in the design. So random relies on a seed, which most PRNGs do, called gseed. And here you can actually see the code that generates gseed. And what a few of you might have noticed is that gseed is only set once. So when you see here, when the server starts, it calls gseed. and we get this time in seconds and the time in milliseconds, and we XOR them together. But then what we do is rather than returning the value right away, we actually set gseed so that every time it's called in the future, rather than calling this function, it just returns that value. So that seed is decided once the server is set and does not change anymore. However, when a new session ID is generated, so when we initialize that random, gseed is updated, and that's what then changes the session IDs that are generated in the future. However, it's updated deterministically, so if you are able to get that initial gseed, you can do all of the deterministic updates and get all the seeds. So what this means is if you do get gseed, you can predict and generate every past and every future generated session ID that was created by that web server. And what this means is if you do know the start time of the server, you can fairly easily get the actual seed and then all the gseeds, or all the session IDs. However, most people don't know that. I mean, Jesse, do you know about that when the server starts?
No.
No, right? Okay. I don't think any of us do. So what we needed to do was we needed a way to go above and beyond that. And without knowing the start time, we had to figure out some way to bypass that. And what we saw was that the top byte changes fairly infrequently. And the reason for that is conversion. Most of you who've dealt with C or C++ have probably seen the horrors of type conversions and what it can do to your code. And once again, it hit this project as well. So as you saw earlier, gseed is generated by XORing the value of the time in milliseconds and the time in seconds. And some of you with keen eyes might have noticed that milliseconds is actually a 64-bit value, while seconds and gseed are both 32-bit values. And for those of you that might see that, here, let me just give you a graphic real quick. So what that means is all that possible space that we would have to brute force is suddenly cut in half, or a lot more than half. But when the XOR value gets set. And what this means is that unlike 64-bit values, 32-bit values are fairly brute forceable with about 4.3 billion combinations. However, that's a bit slow for us. We were not satisfied with 4.3 billion combinations. But as I mentioned, because it uses seconds and milliseconds, the top byte changes fairly infrequently. And it actually changes so little that it only changes every 1.9 days. Which meant that if you knew within 1.9 days of when the server started, rather than the 4.3 billion combinations that you had to try to brute force, it was only 16.7 million combinations. And while knowing that range still is not something that we always know, it does help a lot, especially because you can slowly work your way back from the initial uptime. But don't worry, we didn't just stop there. But before we go into that, let's actually talk about how we were able to crack this at this point. One of the key issues was that in order to find gseed, we needed a valid session ID from the web server. And that's because we needed some way to validate that the session IDs we were generated a session ID that the web server actually had generated, so we had the same gseed. Luckily for us, as I mentioned earlier, the web server can be used to authenticate and manage multiple different control servers, which meant that we were able to set up our own control server and have it authenticate against that. And what you see here is the request and response. So when we have the web server, the valid web server that is managed by somebody else, the target, what we can do is we can send it that post request to log in. We can point it at our web server that we're hosting, and then we can just, or our control server that we're hosting, and then we can just give it the username and password that we control. And then as a result, we get back the valid session ID, which means that we have the first part that we need to actually crack the seed. So now that we have what we need, let's talk about the strategy that we used to actually crack the seed. And we broke it down into 4 major steps. So the first was that we spun up our own version of the web server. And the reason for that is because we're inherently lazy, right? Yeah, I mean, we really don't want to do much work. So we didn't want to, go through and build all of the random and the random string ourselves, debug that. And instead of doing that, spinning up the web server allowed us to use Frida to actually hook into the binary and grab the random initialization and random string functions. So we could let the server do our server do everything for us without having to write extra code. This then let us use these functions to actually replicate the add session function, and we were able to use that to brute force the gseed and then generate all the session IDs. And once we have the gseed, our strategy at the end was basically profit. Just generate as many session IDs as we want, and then take over a server. So let's see a little bit of how that looks like. So Frida, luckily, is great. If you haven't used it before, I highly recommend that you look into it. And what it let us do is, since we had already reversed it, we knew where all the pointers were to all the functions. So we were able to just tell it, this function's at this spot, this function's at this spot, and we were able to grab the functions. Using those functions, we were then able to create our own C module to actually crack it. So we created the ccrack function, which takes in 3 parameters. It takes in the start parameter, or the start integer, and what that is a rough estimate of where your seed is. So let's say you know that the seed was generated in the last 2 days. That start value is going to be the very beginning of those 2 days, XOR, that time period, and then XOR together. And then from there, as you can see, the first for loop just tries to iterate as much as it can until the first byte is changed. However, that can be modified however you need to if there's a longer time period. The second value is the gseed pointer. So gseed is actually a global value, as you saw earlier with how it got changed. And we actually had to change the pointer, or the value at the pointer itself, because the functions didn't take gseed as a parameter. They just accessed the global value inside. And then finally, the third parameter is the target string that we want to get. So we have that valid session ID. We increment the seed over and over, and then we try to generate and check if that session ID is valid. And as you can see here, that internal for loop, we generate 4 session IDs. And I know that there's a few faces, I'll get to that. So we do only try to generate 4, and that's because of the next step. But as you can see here, after we initialize random, just like the add session function does, we then try to create a string, and then we see if that string is equal to our valid session ID. This can then all be called in another function called seedcrack, where we get the pointer to the gseed, we allocate memory for the target string, we crack it, and then once we crack it, we generate the session IDs. So while this was great and it worked fairly consistently, especially if we had just started up the server, which most of the time we had since we were running our own server, there were a few issues still. The first was that the more uncertain the start time of the server was, the longer the computation would take. So, if the server was 40 days old, it took a lot more computational power to get there. And the second issue was that the more time the server was running, the more session IDs that it generated. So this made it harder to predict what session IDs were used for what users, but it also made that we had to brute force more inside that ccrack function. However, luckily for us, Project X had actually done a phenomenal job at securing their system against DOS attacks. So anytime it went down, it would come right back up, and there was really nothing we could do to permanently keep it down. So because it was so secure against DOS attacks, we decided to try to DOS it, obviously. So what we did is we set up a fuzzer, and we actually found 2 different denial of service attacks that would cause the web server to crash. And the crash happened by connecting the official web server to a fake control server that we actually wrote in Python. And the way that it worked is we've almost man-in-the-middle the authentication with our fake control server so that we could do the original authentication, and then once the authentication was done and we were able to talk between the web server and our control server, we sent it a malformed packet that caused the crash. And since the system was so good at coming back online, no matter how we crashed it, it always came online, which meant that every time it came online, gseed was recreated. So rather than having to try to figure out when gseed was made or try to brute force all that time period, we were simply able to crash the server, bring it back online, and then we had to brute force less than 16 million combinations, which is almost nothing. So I mentioned that there's a full attack chain, so I'm going to go over this, just a quick overview. So we have our malicious actor in the original web server. The malicious actor points the web server to our fake server. The fake server then connects back to the web server, crashes the web server, at which point our malicious actor connects to the web server again to get a valid session ID, and then once they have that and have cracked gseed, they'll wait until somebody reconnects to the control server, or their control server to the web server, and then they'll launch the attack. And the reason why we were able to wait until somebody reconnected was because there was a system in place where we could basically ping either the web server or the control server directly and see if a session ID was valid and authenticated. So what would happen is if the session ID wasn't currently in use, it would simply respond saying that nobody's using this, but it would not invalidate that session ID for the future uses. So that meant as soon as somebody actually connected and the session ID was generated, and as I said, we could generate all session IDs, so we knew every session ID that was going to be generated, we could immediately take over their system and do all actions as them. So that was a little bit of that. We had a lot of limitations with this. And what I like talking about, and whenever I talk about vulnerabilities, is the problems we ran into. Because a lot of people just talk about all the great things that happened. And while each of these vulnerabilities was pretty good on their own, we did have a lot of limitations. First, the original command injection. I know we were so happy when we found it, and then we realized, oh wow, it's admin. That's always a problem. So what we decided to do was we decided to try to see if we could bypass authentication. And even that had an issue because you either had to brute force it or you had to have an amount of insider knowledge of when the server was started. And we weren't satisfied with that. So we went further, we reverse engineered, we figured out how to reduce the possible combinations, and then we went above and beyond that even and decided that we would try to crash the server so we could generate it and then have that insider knowledge. So the takeaway from that I want everyone here to have is while one vulnerability may give you what you want, you can probably find others that will give you an even better version to create that full attack chain. All right, so now I'm going to hand it over to my great co-speaker, Jesse, to talk about the hardware side of data centers.
Well, thanks, Kaz. Okay, so on to target number 2. As Kaz mentioned, this is hardware-based. So we're going to be talking about the Avocent KVM. And I've given the model number of the one that we worked with, but this firmware applies to that entire product line. So KVM in this case stands for Keyboard Video Mouse. So effectively, the use case for this is you have a remote admin who logs into their data center, for just to use a general term, using the KVM, and gets a nice graphical user interface to all of their infrastructure, whether that's a Windows server, a Linux box, whatever. It's like RDP on steroids. And so that's the typical use case. You see these used in a wide variety of different data center setups. And interestingly enough, apparently they're particularly popular in telecommunications. Just fun piece of trivia that I came across while looking into KVMs. This particular product line is distributed and maintained by Vertiv, who did a really excellent job working with us to get a patch out quickly. There was a super quick turnaround time of about a month and a half, 2 months, I believe. So I've given the vulnerable and patched versions there, so if you happen to have this lurking in your infrastructure, make sure you update. It's been out for a few months now. And so when we start looking into a hardware device like this, the first order of business is typically to get a better debugging environment than the one that you have just using it under normal operation. So trying to get some kind of root shell admin, access only, unauthenticated, it doesn't really matter. Just we want to be able to install GDB or something like that on the underlying operating system and be able to monitor the behavior of the device a lot more closely. So our first order of business was to figure out how to do that. And so we started looking around the web-based management console and noticed that this device only allows for local firmware upgrades, nothing over the air. So that means that you have to be able to download their firmware that they host on their website and then upload it from your local file system before you can upgrade. So we thought, well, what if we can modify their firmware and add a backdoor and then do some kind of malicious upgrade to allow us to connect to the device and start issuing our own commands on the underlying operating system. So we downloaded that piece of firmware and just sought about trying to understand it. And this is the visual that we came up with. So at the top, there's a small header, custom format, bin walked in, recognize it, just a bunch of metadata. Then there was a Linux kernel, pretty old version, compiled for PowerPC. That's nice. Linux is nice and familiar. And then next, we had a huge region that constituted the file system. And this proved to be the most interesting part. We didn't really care about the rest. So we just snipped that out and got to work performing some surgery. So in order to unpack it, we, as I say, snipped it out and decompressed it. And it turned out to be a SquashFS file system. Now, if anybody out there is not familiar with SquashFS, it's just a format that allows you to take an entire file hierarchy and squash it down into one single flat file. It's nice when you're packaging firmware for download. And notably, this squashfs file system was using a very old version, like 15 years old. So we had to actually download the source code and compile it and make some modifications in order to get it to build. I've included those steps just for posterity's sake. We won't spend too much time on this. But eventually, we were able to get a working unsquashfs binary and extract the root file system. So then it came time to add a backdoor, and we were kind of picky. We had a few requirements that we needed to hit. Obviously, we need shell access over the network, but we also wanted root privileges. We wanted to be able to do anything that we wanted. This also had to be reusable, given that this is part of our debugging setup. We didn't want to have to reboot the device every time we disconnect our session. Similarly, we wanted to have persistence across reboots. It would be lame if we had to update the system every single time with our malicious upgrade. And of course, we wanted it to be low profile so as not to interfere with any of the core functionality on the device and get a really good snapshot of what's going on. So the approach that we wound up going with is to add an init script. So we reversed out the process that happens when the device boots up, the boot up sequence, found that it was invoking this script rc.sh stored in etc, which simply loops over all of the files in the init directory, in this case that's rc.d, and runs them, makes sure that everything's up and running correctly. So we just added our own, leveraging the BusyBox version of Netcat and built-in born-again shell, and had that listen on port 1337, because what other port are you going to use? And that ended up doing the job, or almost. So when we attempted to update our backdoored firmware, update with our backdoored firmware rather, we got an error, wouldn't let us do it. Said something about firmware integrity. So then we had to diagnose why that was failing. And we ended up figuring out that when you click upgrade, this script called firmware check image is invoked. And the most important thing that this script does is to leverage the check image binary against the firmware. And based on the status code of check image, it will either allow the upgrade to continue or it will throw a failure message. And we were getting that failure message. So we figured that this is probably the source of the failed upgrade, as we were, of course, tampering with the firmware. So what we wanted to do was create like kind of an oracle that we could use to fine-tune our backdoored firmware to try and get around this check. So we figured that if we ran check image against a benign firmware and it gave us a 0 status code, and it gave us a non-zero status code when we ran it against our backdoor firmware, it was probably a pretty good chance that this was our point of failure. So we used QEMU in user mode to run check image. Of course, this is PowerPC. I don't have a PowerPC machine. I don't know if any of you do either. And unfortunately, we immediately ran into problems. It turns out that check image relies on a function call that retrieves configuration values from shared memory. We're not doing full system emulation. This is QEMU in user mode. Shared memory was not initialized. So we ended up having to edit the raw binary to effectively create little stubs rather than make those offending function calls, and eventually got our oracle working. And it worked just fine, as expected, against benign firmware, and failed when we ran it against our backdoored firmware. Specifically, it did tell us why it failed. A CRC check was failed in the file system component. So far, so good. We did tamper with the file system. And so it looked like we had found the source of the failure. So now we had to forge the CRC, and in order to do this, we ran check image again, except with debugging enabled, connect to it, and simply set a breakpoint on the instruction which compares the calculated CRC and the one found in the firmware header, and then just dumped those operand values. And it turns out that we were able to get the correct CRC values, and it was simply a matter of splicing that back into the firmware file, the steps of which are shown here. We first of all had to locate where the original one was. Surprise, surprise, it was in that custom header. So we just grabbed the offset and then injected our calculated CRC value into the firmware header in its place. And at that point, check image ran just fine, and we were able to spoof and upgrade. So this is the first CVE that emerged from the research on this device, which is the improper validation of an integrity check value leading to remote code execution. Sometimes you have to get an O-day in order to just start doing the meaningful research. So we just have a quick demo here showing what we were able to do with this exploit. We could log in just using netcat. Running ID proves that we are in fact issuing commands as root, and there's our backdoor running. But as Kasimir said, this is all authenticated, and we're not happy with that. So the next step was to try and bypass authentication. So we took a look at the Nmap output that we did right at the very beginning when we were enumerating the attack surface, and noticed that there is this service that Nmap does recognize called AV Secure Management, which stands for Avocent Secure Management Protocol, and it ended up being vulnerable. So basically, this service supports several kinds of actions used in the operation of the KVM, things like logging in, logging out, so terminating a session, setting up a new KVM session, or doing various network management actions as well, just to name a few. And all of this code is implemented in the main app binary, which does pretty much all of the heavy lifting in the operation of this KVM. So let's just take a quick look at the packet structure for this proprietary protocol. It starts with a 12-byte header, which has the magic number, and the length of the transaction data, the main payload, and the transaction type, which is just an enumeration of the different transactions I've listed there. And then, of course, we have the data itself. So we'll start with the root cause analysis of this vulnerability. All of these packets are parsed using a custom state machine. The hackers in the room will know that whenever you come across a custom state machine, your mouth starts to water. A lot of opportunities for deserialization vulns. And so what it does is it reads the packet header and the data into a single 4,000 hex byte buffer. However, it only enforces size constraints on the transaction data, not the header. So if you max out that data and you send 4,000 hex bytes, you're going to get a 13-byte overflow. 12 bytes for that header that's not accounted for in their size checking, and then an extra byte that was hard-coded in there that we aren't sure of the purpose of, but we'll take it. So this is just pseudocode stripped down of what the state machine was actually doing. It first reads the 12 buffer, or the 12 bytes of the header into the buffer, and then seems to forget that it did that, and then reads 4,000 hex and 1 bytes, thus overflowing the 400-byte buffer. And notice that this is allocated dynamically, so we are living in heap land for this exploit. Keep that in mind, that'll be important. So you're probably asking yourselves, well, what can we do with 13 bytes? That's not very much at all. And you're right, but in this case, we were actually able to create a new user with whichever credentials that we want, and give that user the highest privileges that the device supports. So let's take a look at how we can get there. So there are really only two objects on the heap that we need to worry about. The first is the ASMP connection object, which just holds all kinds of metadata that pertain to that connection, and the buffer that we are going to overflow. The buffer is simple enough, that's just a sequence of bytes, but the ASMP connection requires a little bit of further investigation to understand. This is just a couple of the main fields that we needed to reverse out, and I'll just focus on the most important two. The first is this logged in field, which is just a flag that indicates whether or not this connection has been authenticated yet. So you would need to do a login over that socket in order to set this flag to 1. And then the access level, which dictates what can be done over this connection. Some actions require higher privileges, as I'm sure should make sense to everybody here. So in order to understand how this exploit works, we need to do a little bit of background on the glibc heap. Don't worry, I know it's very dry, we'll be quick. So every time malloc is called, this malloc chunk object is prepended to that allocated chunk of memory. And this just contains metadata for optimizing heap performance and a couple of essential properties, including the size of the chunk that's been allocated. This is necessary for calls like free, so it knows how much memory to free. So this mchunk size field here is what stores that value. So now let's take a look at how the exploit works. We first establish at least 10, preferably more, concurrent ASMP connections in order to make the heap layout very predictable. Main app's very noisy. There are a lot of different actions going on at once. So this was a very reasonable sanity-saving step. And so we only actually use the first two, arguably three, connections. And so we've named those A, B, and C. So the next step is to use our buffer overflow to overflow the buffer for socket A and overwrite the malloc chunk object associated with the ASMP connection for socket B. And what we did there is we set the size to 4010 in hex, which is the size of buffer plus the size of the malloc chunk, which, this is a 32-bit system. Malloc chunk's only 8 bytes, but we're working with 32-byte alignment, so it ended up being 4010. And so now the heap knows that once the ASMP con structure for socket B has been freed, the next allocation of size 4000 that it needs to make should be placed at that spot. This is just a feature of how the heap works for optimization purposes. So next we issue just a benign logout transaction in order to cause socket B to close gracefully, thus freeing the buffer, and then freeing this enlarged ASMP con structure. So some data is being freed twice, that's not a problem. The point is the heap knows where to put the next buffer. So the fourth step is to open up a new connection, socket D, and now ASMP con is located where the previous buffer was, and the buffer is now located where the ASMP connection struct was. So they overlap due to this monkeying that we've done with the heap, and this is very important. To set up our final payload, which uses all of the space available and fills buffer with the SNMP instructions to add a new user with whatever username and password we want and the highest possible privileges. We also elevate the privileges of our own connection object, setting the logged in flag to true and the permissions to 3, which is the highest permissions that they add. And that is enough to allow us to add a new user. So let's see that in action here. I'm just logging in using the default credentials. This is totally fair game. And if we go to the users, we see that that is the only user there. And so now I'm going to run the exploit, just give it the IP, whatever username I like, and the password. So now that the exploit's been run, I can log in with that username and password. You can see in the top left of the window that I am logged in as that user, and the user has been successfully added. However, there was a bit of a facepalm moment when we realized that we could have accomplished the exact same thing with a null byte injection on the login page. So that was one of those cry and laugh at the same time moments. So there is a vulnerability in the login mechanism due to the fact that anonymous sessions are supported on this device just for internal purposes, and if you give it a null byte for the username without any password, it just assumes that you're trying to do one of those local connections and will log you right in. So nice short exploit, and as you can see, when we dump the user file for that login, you can see no password. It's an anonymous session, -1 for the user ID. And so this was our third vulnerability for this on this device, which is just a null byte login, authentication using an alternate path. So now I'm going to turn it back over to Kaz to take us away.
Thank you.
Home, rather.
So we want to leave you guys with a few concluding thoughts. I hope you guys enjoyed everything, but there's always, a few bits of wisdom left. The first is that authentication alone does not justify weaker security. We have both been researching for a while, and almost every single device that we see, if they assume it cannot be externally accessed or it's behind some sort of wall, they just pretend like security doesn't even exist. So please, uphold that internal component with the same standards as the externally facing components. Another thing is that those convenience features or As Jesse discovered with the firmware upload, the inconvenience features can often be abused for exploitation. So before turning features on by default, consider the potential security impact. A lot of times we see that there will be a feature on by default, or there will be a feature that isn't on. And then in the docs, they'll say, if you want to make this secure, please do this or that, rather than it being on by default. And then finally, data centers are really attractive targets. As Jesse mentioned earlier, they have high impact. A lot of components are externally facing. So really great projects to work on. We also wanted to give a few acknowledgements. So Jesse and I both worked on this project while we were at Trellix Arc, and we worked on it with Sam Quinn and Austin Emmett, who are both amazing researchers if you ever have the chance to work with them. Thank you for coming to our talk.